let's talk about non-separable data. And as we see on the right, there are these two kinds of non-separability. Okay, so on the left, we see that the data is essentially linear, maybe some measurement errors. And so we would like to maintain a linear separator, but tolerate error. On the right, the problem is nonlinear. We need something else. We can't do it with linear. Okay. Now, for the situation on the right, we already discussed this at length when we talked about the nonlinear feature transform, when we talked way back about linear models. Well, the optimal separating hyperplane is just a linear model. So, we can use all the machinery of the nonlinear feature transform for the situation on the right. So how does that work? So you have your data, okay, you transform to your z-space, okay, and, you pick your favorite linear model algorithm to produce your linear separator, your hyperplane. Well, now our favorite algorithm is the FAT separator, the optimal maximum margin separator. Okay, so you just run your quadratic program in your, z-space instead of the PLA. Okay? And all that discussion, all the machinery of the nonlinear transform works. Seamless. Okay? When you get a test point, you transform it and use your linear separator in the z-space to classify. So we don't need to spend too much detail on that. Okay? There's no difference. It's just that the algorithm that you deploy in the z-space is this quadratic program. So we need to focus most on the situation where we want to tolerate error. Okay? And so let's develop what's called the soft margin optimal hyperplane. So the soft margin optimal hyperplane. Okay, so this suggests that what we've been discussing so far is not the soft margin optimal hyperplane. Indeed, it's called the hard margin, optimal hyperplane. So you think you've got your hyperplane, it's got a thickness, and you try to separate the data with a fat hyperplane. Okay. And it's hard margin because you have to separate the data modulo that thickness. Okay. Now, if the data is not separable, you can't separate, with the thick hyperplane, let alone with a thin hyperplane. Okay. So you have to allow the data in some sense to penetrate that thickness, that margin. And so that's what makes the margin soft. Okay. Now, in order to sort of figure out the algorithm, let's first write down the optimization problem, the quadratic program that we had for the hard margin, hyperplane. Okay, so what were we doing? We were minimizing, so we said we're going to minimize, okay, the norm of the weights, okay, subject to separating the data. Okay, that's essentially what made it the hard margin. Subject to yn w transpose xn plus b is greater or equal to 1. And this 1 being a positive number, you could have put any positive number you wanted, but we chose 1. This 1 being a positive number, this is the constraint that enforces separation. Okay, so let me show you what that looks like with some data. So let's say you have, some data, so some zeros, some blues, and some reds. Okay, and some reds. Okay. Now when you solve this quadratic program and produce the fattest separator, you will get something like this. Okay, and here's the margin. Okay, and you can imagine, we start the margin at this separator and grow the margin, and eventually it hits simultaneously these blue points and these red points, and that's necessarily going to happen for the optimal fat separator. Okay, and the sort of definition of the points that are on this margin are the ones that saturate this inequality. In fact, we argued that when you solve this problem, the minimum over n of yn w transpose xn plus b is going to equal 1. In fact, this was the definition of separability, and then it produced this optimization problem. Okay, so it means that some data points accomplish 1. Okay, for this constraint, and all the others are strictly greater than 1. Well, which are the ones that accomplish 1 are the ones that are on the cushion, that are the support vectors that prevent it from expanding. So the 1 is coming from these points, okay, the support vectors. These guys are the ones which saturate this constraint, that make it equality. Okay. Now let's look at the situation if the data is not separable. So let's put a blue 0, a blue O here. Okay, now the data is not separable. And you can see, so for these points, this quantity is 1. For these points, it's strictly greater than 1. Okay, for these points, it's 1. For these points, it's strictly greater than 1. For this point, this is going to be less than 1. Okay, in fact, it's going to be 1 minus something. So it's penetrated this cushion. So it's going to be 1, and I'm going to put in green, let me put in green, it's going to be 1 minus an amount by which it has penetrated the cushion. Let me call this C. Okay. And this penetration is indicating the fact that this, fat separator is not separating this data point. It has had to penetrate the cushion. So this quantity will be strictly less than 1. Okay. And so if we're going to allow non-separable data, then we should not enforce the constraint that this has to be greater equal to 1. So equal to 1 for the support vectors that are preventing the cushion from expanding. Greater than 1 for the points that are more than separated by the thick margin. And the points that are not separated by the thick separator will have less than 1. So for each point, we'll allow an amount of penetration, an amount of non-thick separation. Okay. So instead of requiring this to be greater equal to 1, we will require this to be greater equal to 1 minus Cn. And each data point is allowed to penetrate. Okay. And we will say that these data points don't penetrate. These data points also don't penetrate. Okay, it's only this data point that penetrates. So we will require that Cn be greater equal to 0. Okay. Now, how much does each data point penetrate? I don't know. I'm just allowing it. So I need to figure out how much each data point penetrates. Now, if we just solve this problem, it turns out that what you will do is you will send all the Cn's to infinity and send the weights to 0. So in other words, you'll just say, I can minimize the norm of the weights by allowing all data points to penetrate, and I'll get an infinitely wide margin. But it's useless because all the data points have infinitely penetrated. Okay. So I need to somehow penalize penetration. I don't want too much penetration. I only want penetration when it's absolutely necessary. So I can't just minimize the norm of the weights. I have to penalize, the sum of the penetrations. So I have to somehow penalize, and we'll choose to penalize the sum of the penetrations. And, the amount by which we penalize the penetrations, let's call it a constant C. Okay. And so if I solve this optimization problem, what am I doing? I'm asking for the weights and the bias that separate the data with some thickness, but allows penetration of the cushion, by a certain amount for each data point. Okay. And I've, in some sense, tried to minimize the sum of the penetrations. So you can think of the sum of the penetrations as an in-sample error. An in-sample error with respect to the fat separator. Okay. And you can see what we're doing is we're trading off the fatness of the separator with the in-sample error. The fatter I try to make my separator, the more penetration I'm going to get. Okay. And so we say that this optimization problem, when you solve it, is the soft margin optimal hyperplane optimization problem. So if we solve this, we produce the weights and the bias that in some sense gets you a fat separator with minimum sum of margin violations. These are called margin violations. And from the optimization perspective, these are called slack variables. Okay. So in this optimization, let's look at what are the variables. The variables that you have to determine are obviously the weights and the bias, but also we don't know how much each data point, violates the margin. So you have to also determine the C's. So you minimize with respect to the weights, the bias, and the C's. Okay. And minimize this optimization. Now let's compare this with some of the things that we have already seen. What are we doing? The objective that we're minimizing is, in some sense, an in-sample error plus the size of the margin. Okay, so this is in some sense inversely related to the size of the margin. And since we're minimizing, we're trying to find as large a margin subject to a small in-sample error. Okay. We saw something like this before when we did regularization. We were minimizing the in-sample error plus a penalty term. Then it was a penalty for complexity. Now this is the size of the margin, the robustness to error. So this is now just like regularization. And indeed, C plays the role of a regularization parameter. Okay. So large C means you're focusing more on the in-sample error. So you could potentially overfit more. Focus more on in-sample error. Okay. Small c means you're focusing more on the margin. You're focusing more on robustness. So small c means more robustness, more ability to tolerate measurement error, more robustness. So more regularized, small c. Less regularized, large C, if we want to put it in the language of our foundations. Okay. C goes to infinity, okay, means that you're exclusively focusing on the margin violations, and you'll send all the margin violations to 0, which can only be possible, when the data is separable. So this recovers the hard margin when data is separable. Okay. So this is the optimization problem that allows us to effectively run find a thickest possible separator while minimizing the sum of margin violations. And how much attention you pay to the sum of margin violations is determined by the parameter C, which we get to pick. Okay. And as we will see shortly, this plays the same role as a regularization parameter. And so it's an important parameter to pick, and it has an effect on what happens. Okay. Now, when C goes to infinity, when C goes to infinity, you recover the hard margin, and it's only possible when the data is separable. But it's still plausible that even if the data is separable, you may not want to use C goes to infinity. So you may not want to use the hard margin. Now let me give you an example of that. Okay, so let me just give you an example of that. So let's say here's your data. Okay, I'm going to draw some x's. Okay, a nice separable data, some blue O's, approved credit, nice and separable. And let's say that there's an X over here. Now, if you focus on the hard margin classifier, you have no choice. Okay, you're going to try to find the maximum margin separating hyperplane. So it's going to do something like this, and this is going to be its margin. Okay, but now if you think about this, okay, so if you look at this, and let me erase now this separator that we picked. I'm erasing this separator. Let me put back my data. 0, 0. Okay, this guy, X. Okay. Now if you look at this data, you might think, wow, this looks very weird. Maybe this person was accidentally defaulting on credit, and that's why he got a red X. Maybe he fell down a cliff or something. Okay, so should really have been given credit based on the features. Okay. Now you could go and look through the data and try to figure out which ones are misclassified, or you could say, you know what? Let me run the soft margin classifier, even though the hard margin would have worked. And the soft margin will say, you know what? I can get a huge margin by putting my hyperplane here. I can get a huge margin, and what's going to be the margin? The margin is going to be this. I can get a huge margin. Okay, but this data point has penetrated a little. For the price of a little bit of penetration, I can get a huge margin. So there can be some, and then this looks like a much more robust hyperplane. It makes an in-sample error, but we suspect when we look at this example, we suspect this might be an actual error, not an in-sample error. So this may be correct. Okay, but instead of the soft margin classifier will automatically take that into account. It'll say I can get a huge margin with a small amount of penetration. And so even though the data is separable, we may still want to use a non-infinity, a small value of C. Okay. So now let's look at some results. Okay, and here is some data. Okay, and I'm showing you the difference between C equals 1 and C equals large. C equals something like 500. Okay, and so we see that when C is small, we're focusing more. This doesn't have as large a contribution. We're focusing more on the width, and you get a wide. That's this yellow region. You get a wide. You get a very thick separator with lots of penetrations. Because when C is small, we don't care about penetration. We're focusing mostly on the thickness of the classifier. As we increase C to 500, you see the margin shrinks and there's a lot less penetration. Okay, and that's expected. That's exactly what we expect when we solve this problem with a large C. Okay, so the choice of C is important, and it trades off in-sample error with the thickness of the hyperplane, robustness to measurement error, regularization. Okay, and here's the situation when the data is separable. Okay, just like what we just illustrated, and you can still choose, C not infinity, so you can still choose to use the soft margin hyperplane. If you choose C too small, then you can it's a situation like this, where the data is separable, but, the final classifier misclassifies this data point. Okay, and if you choose C medium, reasonably large, okay, then, you get you get a slightly thinner classifier, and the data gets correctly classified now. And if you choose C very, very large, you recover the hard margin classifier. Okay. And so the choice of C is important. It's an important parameter that has to be chosen. It is effectively a regularization parameter. It tells you, because what are we? We're in the game of tolerating in-sample error. Okay. And we need to precisely define what it means to tolerate the in-sample error. And that's what this parameter C quantitatively defines. What do you mean by tolerate in-sample error? Tell me explicitly, how much do I penalize margin violations? Okay. But the nice thing is that this problem, you might ask, how did I get these solutions? This problem, and now this is an exercise for you, is also a quadratic program. So this is also a quadratic program. Okay. So there. That's how we tolerate error. We instead of using the hard margin support vector machine, instead of using the hard margin optimal hyperplane, which is this optimization problem without the red parts, we use the soft margin optimal hyperplane. And now, when you use the soft margin optimal hyperplane, you have to pick the regularization parameter C. So let's briefly have a look at some results and discuss a little bit, the second kind of, that we showed over there, the second kind of non-separable data, the one where we have to use the nonlinear transform. Okay.